So, so far in our lecture, we've been discussing primarily qualitative approaches to identifying the lowest and highest energy conformation of a given molecule. What we're now going to do is focus on some quantitative approaches where we're going to draw Newman projections for a given molecule as a function of and looking at each conformation across various dihedral angles. And then we're going to calculate the energy for each conformation. And from this, we'll be able to generate a plot of energy as a function of dihedral angle. And in turn, we'll be able to identify the lowest and highest energy conformation of a given molecule. As we discussed, the notable conformations will vary from 0-degree dihedral angle all the way to 300. So we have 0, 60, 120, 180, 240, and 300 degrees. We don't need to include 360 because that's just the 0-degree conformation once again. So what I want you to do is before we discuss this example, I'd like you to pause. I'd like you to take some time to draw the Newman projections for this molecule. Look at the Newman projection for each bond rotation for the dihedral angle changes. So I want you to draw the Newman projections for 0, 60, 120, 180, 240, and 300. You can pick any two groups for your dihedral angle calculation. Just make sure those two groups are kept consistent. And then I'd like you to tell me from your plot what the highest and lowest energy conformation of this molecule across the AB bond is. So pause the video, work through that, and we'll discuss momentarily. Okay, so first and foremost, we need to draw a Newman projection. We're going to view this molecule looking down the AB bond. Carbon A will be in front, carbon B will be in the back. Both these methyl groups have a wedge, so they'll be on the right. The hydrogens, which are implied, have a dash, which will mean they'll be on the left in our Newman projection view. This ethyl group is pointing up. Oh, let me see one more time. So looking at this carbon-carbon bond, this ethyl group is below the carbon-carbon bond, so it'll be down. This ethyl group is above the carbon-carbon bond, so it'll be pointing up. So we have our first ethyl group, the methyl group, and a hydrogen. Next, we have the back carbon ethyl group, the methyl group, and a hydrogen. From here now, we're going to pick two groups. I'm going to pick these two ethyl groups. It's generally good to pick the largest groups. And I'm going to draw them with a 0-degree dihedral angle. To accomplish this, I'm going to rotate my front substituents 180 degrees. This gives me the ethyl group, the methyl group on the left, and the hydrogen on the right. The back substituents stay the same. Just as a check to make sure that we didn't accidentally invert our stereochemistry, what we're going to do is we're going to check to make sure that the relative position of our substituents is consistent. So how are we going to do that? First, drawing a clockwise arrow, we see that counting our substituents clockwise, we have an ethyl group, then a hydrogen, then a methyl group. Checking clockwise, we have an ethyl, then a hydrogen, then a methyl group. So we effectively rotated our carbon-carbon bond without accidentally changing or swapping our substituents. Okay, now let's take a look at the interactions. These are eclipsing interactions. This is going to be our 0-degree Newman projection. So in terms of eclipsing interactions, we have an ethyl-ethyl eclipsing, which is about 11 kilojoules. We have a methyl hydrogen eclipsing, which is 6 kilojoules. and another methyl hydrogen eclipsing, which is 6 kilojoules. Okay, let's now rotate. We can rotate our front carbon 60 degrees, and let's generate the 60-degree Newman projection. In this case, we still have the same relative position of our substituents. Again, ethyl, hydrogen, methyl in a clockwise arrangement. From here now, for 60 degrees, we had to take a look now and talk a little bit about the gauche interactions. So in terms of the gauche interactions, we have an ethyl-ethyl, we have an ethyl-methyl, and we have two of those. The ethyl-ethyl is about 4 kilojoules, ethyl-methyl about 4 kilojoules times 2. So in total, we have 4 plus 8, which is 12 kilojoules of strain, compared to about 23 kilojoules of strain in our 0-degree fully eclipsed structure. Okay, we're going to rotate our carbon-carbon bond 60 degrees once again. In this case, let's draw out the 120-degree conformation. So we have our methyl group, the ethyl group, and the hydrogen. This time, the methyl group and ethyl group are eclipsing. We have that eclipsing interaction twice, and the hydrogens are eclipsing. So looking at the eclipsing interactions, we have a hydrogen-hydrogen eclipsing, which is 4 kilojoules, and a methyl-ethyl eclipsing, which is going to be about 11 kilojoules times 2, which gives us about 26 kilojoules of total strain. Now, you may be wondering why the 120 degree happened to be higher in energy than the 0 degree. It stems from the fact that methyl and ethyl groups are pretty close together in size, and in this case, you get far more strain by eclipsing the most large groups with one another. So this 120-degree conformation is going to be tentatively labeled as the highest energy conformation. And this really demonstrates why sometimes it's important to be able to go through this kind of rigorous analysis where you look at all of the different conformations and check the energy. Because in some cases, your initial guess of what the lowest and highest energy conformation will be may not hold true when you do the calculations for all the conformations. Okay, let's look at what happens if we rotate our carbon-carbon bond another 60 degrees. This gives us the 180-degree Newman projection. From here now, we have some gauche interactions. We have an ethyl-methyl. We have 1, 2 of those. And we have a methyl-methyl gauche interaction. So this is about 4 kilojoules times 2 and 4 kilojoules, which gives us 12 kilojoules in total. I would say that this conformation, if we just compare these, the 180 and 60 degrees, an ethyl-ethyl gauche interaction is going to be a little bit higher. So this is probably going to be closer to 13 compared to the 12 calculated if we just have a methyl-methyl gauche interaction. The difference between 60 and 180 is subtle but notable. This is why I like to list out the different interactions because it makes it easy to see the difference in energy. Continuing rotating, let's look at the 240 degree. So in this case, we have our front methyl, our front ethyl, and the hydrogen. Let me redraw this for a little bit better depiction. Okay. From here now, let's take a look at the eclipsing interactions. We have an ethyl hydrogen eclipsing, which is about four, no, not four. That would be hydrogen, hydrogen. So let's erase that. Closer to 6 kilojoules. We have another ethyl hydrogen eclipsing, which is 6 kilojoules. And then we have a methyl ethyl eclipsing, which is going to be around 11 to 12 kilojoules. So in total, this gives us around 23 to 24 kilojoules of strain. Okay, let's look at our last conformation here. Rotating another 60 degrees gives us the following. Again, we're only rotating our front carbon substituents, keeping the back carbon substituents exactly the same. Here we have some gauche interactions for this 300-degree conformation. We have an ethyl-ethyl gauche interaction, which is about 4 kilojoules, and we have a methyl-methyl gauche interaction, which is also 4 kilojoules for 8 kilojoules of total strain. So it appears, let me just make a tally of what's happening here. So it appears in this case, the 300 degree is our lowest energy conformation, while the 120 is the highest. So if we're filling in our plot of energy as a function of dihedral angle, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Okay, let's now plot this. So the 0-degree conformation we established to be about 23 kilojoules per mole of strain. So somewhere around here. The 60-degree conformation is around 13, about here. 120 was around 26, about here. 180 was around 12, about here. 240 is about 24, is about here. And finally, 300 was around 8 kilojoules per mole of strain. We'll then connect the curves. One moment. Let me just redo that. So 60 is around 13. 120 is around 26. One 80 is around 12. 240 is around 24, and 300 is around 8. So let's connect the line. And there we go. One moment. So in this case, the broader curve. Let me add the points in, and then let's draw out the full curve. I'm going to connect them with a dotted line just to show the curve. There we go. So now we have a full plot of energy versus dihedral angle, with the highest energy conformation being 120 degrees and the lowest energy conformation being 300 degrees. So this is an example of a full Newman projection analysis and conformational analysis question, such as that you would see on a typical exam. To close out this lecture, I'd like you to review and continue to engage with the Newman projection examples, and we're going to talk about one additional topic, which focuses on hydrogen bonding. So continuing on with the Chapter 3 lecture discussion, we're going to complete the Chapter 3 discussion by talking a little bit about hydrogen bonding and Newman projections. Hydrogen bonds are strongly stabilizing interactions, providing about 20 kilojoules per mole of stabilization. Common hydrogen bonding groups include alcohols, amines, carboxylic acids, and amides. Structures capable of intramolecular hydrogen bonds prefer to place hydrogen bonding groups gauche to one another. Why is that? And what is the motivation behind that? Well, for structures capable of hydrogen bonding, the gauche conformation is typically lower in energy than the staggered conformation because this intramolecular hydrogen bond provides around 20 kilojoules per mole of stabilization, which overcomes the destabilizing gauche interaction. Compared to the anti-conformation, which has no hydrogen bond between these two groups, there's no intramolecular hydrogen bond. As a result, the anti-conformation is higher in energy because it lacks that stabilizing intermolecular hydrogen bond. Now, hydrogen bonding is great and all, but we still don't want to place our substituents eclipsed. We want to place the hydrogen bonding substituents gauche, so they're close enough in 3D space, separated by a 60-degree dihedral angle, and thus these two substituents can hydrogen bond, and we can stabilize our molecule through that hydrogen bonding interaction. So for example, if we have to draw the lowest energy conformation across the Ca-Cb bond in the following molecules, you're always going to want to make sure if you have hydrogen bonding capable substituents, you're going to want to make sure that those substituents are gauche to one another. For this second example, let's look instead at this carbon AB bond, just as I found it's a little bit more interesting. Now, taking a look at this first example, we see that the amine and the alcohol both have a wedge. The implied hydrogens have a dash. We're going to look down, looking with carbon A in the front. As a result, every substituent with a wedge ends up on the right. Every substituent with a dash ends up on the left. And these two methyl groups are below the carbon-carbon bond, so they'll be pointing down. So in this case, we have our methyl group, the amine, and the hydrogen. Next, we draw out the second methyl group, the alcohol, and the hydrogen. Now, I just want to caution you that even though the amine and alcohol are close in 3D space, this is the eclipsed conformation. And the eclipsed conformation has too many destabilizing steric interactions to be the lowest energy conformation. So instead, what we're going to do is we're going to rotate the back substituent 60 degrees, and we're going to draw the gauche conformation. In this case, here, the alcohol and amine are separated by 60 degrees. They're gauche to one another, and as a result, they're able to hydrogen bond. This gets us the best of both worlds in that the substituents are close enough to hydrogen bond, but they're not eclipsed with one another. Now, this is option one. There is another option for a gauche conformation that has hydrogen bonding. If we rotate our substituents 120 degrees, we get the following secondary possibility. How do we decide? Well, let's just make a list of interactions. In terms of gauche interactions, in option number one, we have the OH amine gauche interaction. We have the methyl amine and a methyl methyl. For option number two, we have the same OH amine gauche interaction as we should. We have a methyl methyl and a hydroxyl methyl. The only really difference is the fact that in one of these structures we have a methylamine gauche interaction, and in the second structure we have a hydroxyl methyl gauche interaction. These two structures are very, very close in energy, and either of these responses would be acceptable for the lowest energy conformation. If I had to pick, considering the bond length and the overall amount of space each substituent takes up, the hydroxyl group is slightly smaller. So we'd have a minor preference for placing the hydroxyl group adjacent to these larger multiple substituents. It's a very minor difference. Key thing, rather than drawing the anti-conformation, because our substituents can hydrogen bond, we choose the conformations that place the hydrogen bonding substituents gauche to one another. With that in mind, I'd like you to apply what you've learned, and I'd like you to draw the lowest energy conformation for this second molecule. So pause the video at this time, and then we will discuss this example momentarily. Okay, so first and foremost, we're going to draw out the hydrogens. Next, we're going to draw out our front carbon. Everything with a wedge ends up on the right. Everything with a dash ends up on the left. The alcohol is pointing up. The carboxylic acid is pointing down. So we have one goal in mind. We need this carboxylic acid and alcohol gauche to one another. To this end, we're going to rotate our back substituents 120 degrees, and that in turn gives us the following conformation. So with that, we've drawn out the lowest energy conformation. Again, anytime you have a hydrogen bonding substituent, you want to place the two hydrogen bonding substituents gauche to one another, as hydrogen bonding is so incredibly stabilizing that in the majority of the cases, it overcomes the destabilizing gauche interactions. So that concludes our discussion of the Chapter 3 topics, and we'll be continuing this lecture series as we move on to Chapter 4.